Hello everyone, and welcome to another episode of Engineer's Corner. Today's episode is the second in a series on statics, and we're going to be talking all about moments. So what exactly is a moment? Well, you create a moment every time you flip a light switch or open your refrigerator door. A moment is simply applying a force on an object at a distance away from its hinging point. So take this cantilever beam for example. This beam is mounted to a flat surface, such as a wall, and attached with an adhesive or weld or something of that sort. But it's important to note that the beam does not penetrate the wall. The surface of the wall is uniform throughout, and the rod simply attaches to it. So we're going to refer to this side of the beam as our fixed end. Now the other side of the beam here doesn't have any surfaces pressed up against it. It doesn't have anything obstructing it from moving up or down like a support. So we're going to call this the free end. Now we take our beam here and we measure it from the fixed end to the free end, and we find that it is a distance L. Now at the very end on our free end we're going to apply a force F. Now this force is going to push down on our beam and cause it to bend, thus creating our moment. Mathematically we can describe a moment as a force applied over a distance, or distance times force. Now our distance here is L, and our force is F. So we can say that our moment is equal to L times F. Now let's say that we applied a bigger force at a distance x away from the fixed end. Now this distance x is shorter than L. Thereby we need to increase our force G if we wanted to achieve the same moment. But if we balanced them right, we could create the same moment from our force G at a distance x that we could by applying a force F at a distance L. So if we apply our force F at a distance L, we're going to create a clockwise moment on the beam. Now remember, this arrow could be faced this way or this way. And remember, in statics we don't want anything to move. Thereby we need to create a counterclockwise moment to cancel out this clockwise moment. And we can do that by applying a force here. A force of G applied upwards would create a counterclockwise moment. And this counterclockwise moment, if our force G was large enough and our distance x was small enough, we could create the same moment here, and thus the sum of our moments acting on the beam by the forces would equal 0. So let's take a look at this example here. Let's say we want to apply a force at a distance of 24 inches away. This is going to be the entire length of the beam. And we're going to apply a force of 140 pounds. Now this 140 pounds is going to create a clockwise moment on this beam. So we're going to apply an upwards force here on the beam, which will create a counterclockwise moment. So we know that our force here is 336 pounds, and we're left to find the distance x and the moment that's going to be acting on this beam. So if we remember, a moment is simply a distance times a force. So if we plug in 24 inches for L and 140 pounds for F, we find that the moment created on our beam is 3,360 inch-pounds. Now an inch-pound is a unit of bending force, such as a torque. We need to create the same moment here, but in the counterclockwise direction. So we can say that our moment is equal to our distance x times our force G. If we substitute 336 pounds for G, and we say that our moments must be equal, then we can simply divide by our force, and we find that x is 10 inches. So if we apply 336 pounds at a distance of 10 inches, then we will create the same moment as 140 pounds applied at a distance of 24 inches. So let's look at a little more complicated example here. We have your common seesaw, and we're going to apply a downwards force of 100 pounds at 8 feet away. Next we're going to apply 50 pounds upwards only 4 feet away to the left. We're going to apply another force of 200 pounds 3 feet away. And finally, we're going to apply our final force 5 feet away, but we need to figure out what this force is. So if we look here, we have 100 pounds. That's going to be creating our counterclockwise moment here, right? If we look at the center of our mass here, which is this hinging point on the beam, then this is going to push down and thus want to make the seesaw rotate like this. Now if we look at this force, this is actually going to go in the opposite direction. This is going to want to make this end go up and this other end go down. So the 200 pounds, while it's pointed down, you might think, oh, well, that must be acting in the counterclockwise. It's because it's on the right side of this hinging point that it pushing down actually creates a clockwise moment. And so that means for F, it's actually going to be the opposite of this 50 pounds. That's going to create a counterclockwise moment since we're pushing up and our seesaw is going to want to raise on this end and lower on this end. So let's move our problem up here. We want to take the sum of our moments, or the sum of our forces acting on the beam, and we want to sum those equal to 0. So remember, a moment is a distance times a force, and we want all of our moments to total to 0. Basically what we're saying is we want the counterclockwise and the clockwise moments to cancel each other out. So for our sign convention, we're going to say that a counterclockwise moment, such as this 100 pounds, or as this F here that we'll be looking for, those are going to be positive moments because they're acting in the counterclockwise direction. Now our 50-pound force and our 200-pound force are going to both be in the clockwise direction, therefore we're going to label those as negative. So our first moment here is at a distance of 8 feet times 100 pounds, and since it's clockwise, we're going to say that's a positive moment here. All right, so our next one is 50 pounds acting 4 feet away. And remember, that one's in the clockwise direction, so we're going to say that this value is negative. Moving on to our 200 pounds acting 3 feet away. Again, this is going to be acting in the clockwise direction. Therefore, we're going to say that this quantity is negative. And finally, we have 5 feet times our unknown force F. And that's in the counterclockwise direction, therefore that's a positive value. Remember, all these together have to equal 0. So we find that our first moment is 800 foot-pounds. Our second moment, created by the 50-pound force, is a negative 200 foot-pounds. Our 200-pound force is going to create a moment of negative 600 foot-pounds, and we still need to find this value of F here. Well, if we notice, we have 800 minus 200 minus 600. That actually gives us 0. So we find that our force here is 0. And what does this mean here? So basically we're saying that we don't need any other forces applied to this seesaw, that our seesaw is perfectly balanced. So we have 800 foot-pounds, negative 200 foot-pounds, and negative 600 foot-pounds. And we can say that our sum of moments is equal to 0, or our system of our seesaw and applied forces is in equilibrium. Thank you guys for watching, and stay tuned for the next episode concerning torque.